who's here. Come.
Sir, I got a mail from advisor regarding that you will need to put marks. So by today I will pay the invoice.
Okay.
They'll send us.
Okay.
Yeah.
Ask Paul to contact me.
Yeah. How was the vacation, sir?
I can say well.
Same.
I did a lot of things. Oh. Strange. And then not too much students on the list.
Today?
Yeah, by the way, I don't see you in seven. I'm looking 703, but I need you will be in. Yeah, again split. There are two cars if it's the same name.
Yeah.
1703, 16635. See, you attached to 635.
Yeah, that.
And on an email one attached to old one.
Okay.
That means what I need.
We have some new students?
Good question. I don't think so.
No, just 3 only.
And email
Name
attached to old course.
Okay. Is he having thesis?
I can tell 100%, but appears what no. Okay, I need to.
And this time you were for thesis.
I will substitute because Professor Sultan ill. I will substitute him for. I don't know for this semester or for some time. I can tell. I don't know how well. How it depends on health. On Professor well-being. I'm hoping it's for short time.
So you are for different subject.
Yeah, it's not my course, but because Professor suddenly got ill and someone need to substitute.
Yeah.
Okay,
That
I
is
say
why-
okay for this time.
Yeah.
I'll take this course because I had space in my academic load. Okay, anyway, I need to do. I need to do this. So. Professor. Hello, hello. I'm talking with online. Hello, hello. I will start. And now. No. Anybody here? Not us. Okay, let's do something. Let's do something. Here, my board. So this is new electronic device of power system. I'm a substitute here. I'm substituting Professor Ten. Oh. Run, you wait. So, I'm substituting, remove camera, Professor Sultan for this. Yeah, I hope it will be well, but we are where we are. So I need to start. Name of this course is Electronic Devices of Power System. So what kind of devices are where we are, what we are talking about? Of course, there are many and multiple electronic applications. I will point with my finger key types. First, closest to mine, it's my area of research, are protection devices. So, we have some systems. It may be we are unlucky, it's fault. So we need device taking currents, taking voltage, taking some information. Here, for voltage, taking some information and detecting what fault condition. If fault condition is detected, so this is protection, signal to disconnect should be sent. Fault protection device. It's my area. Devices monitor condition, take voltage, current, do some processing on them to determine good or not good, fault or healthy. If there is abnormal condition, faulty part should be disconnected. More complex devices are for system stability. This kind of device we can like a cloud. Multiple large system with multiple generation source and so on. So if there is fault, special devices are able to isolate faulty part, disconnected from system to maintain system stability. Devices for maintenance of system stability. More complex, more because they, how to say, more important burden of responsibility, if I can use it, for such devices is much higher. These devices are more complex and of course more expensive. This kind of electronic device. Special kind of devices are fault locators. So if there is a fault, such kind of device should be able to answer where the fault is, to point fault distance, fault location. Fault location devices, special group of devices. Also, what can I point? Devices to maintain voltage control devices and more general reactive power control devices. For example, simple device takes voltage, gives commands to stepper, to tap, it's called tap changer, to change power of transformer rating. To change transformer rating. Automatic voltage control. Voltage control devices, reactive power balance control devices. Maybe in more simple form, switchable capacitor banks, devices controlling capacitor banks to maintain balance of reactive power. Thus voltage can be controlled. Nowadays, very complex things. What we got, for example, wind parts or array of photovoltaics. Middle voltage network, transformer, gateway devices. Now I can mark them as gateway devices, ensuring energy flow from photovoltaics or wind farms to the network, low voltage or middle voltage distribution network. Quite complex device. Deeper, I hope I will have time to speak about them. Systems where, for example, we have photovoltaic, we have battery storage, we have connection to distribution network, gateway device ensuring two-dimensional power flow both from and to. And okay, there is not enough space. This is customer. And supply to customers. Complex devices ensuring two-directional power flow, storage, and because there is one moment for such kind of system. Smart device. Wind is irregular. Sun activity more regular, easier to predict, but also non-regular. Never, really never, demand for power corresponds to peaks of production, both for wind and sun. You need storage, but that's not all. One of the serious thing, owners of such system always eager for profit, and they are trying to adjust to what? To price markets for electricity. So, idea with storage, not only battery at daytime where we have sun energy, then use it for charge for EV cycle at night. It's too simple. Such systems are usually adjusted with eager for profit in mind, so they try to maximize profit, and maximum peak of profit means what? You always consider buying from the network by market price. Quite complex device. What else? Special kind of device are monitoring and metering devices. Energy costs money. The money you need accounting. One group, smart meters, not only counting of energy, customer control, paying discipline enforcement, prepaid meters and some things like this, and more trending analysis, deeper analysis. Why? First, power companies try to optimize their generation profile. When you speak about local company, they always are in kind of crunch between customer demand and push from the market to get how to say, to get ability to develop optimal strategy. Trading now, trading tomorrow, generation. For example, should we spend water in water storage in our reservoirs now, or wait for some time? Companies always try to, balance the generation profile, including import profile part, and they are eager for customer behavior, customer demand prognosis. Smart metering, good smart metering allows you to get data base. Yes, it's another area of big data to try establish demand prognosis and demand tendencies. It's a question of development for companies. So good metering with communication, metering allowing to create customer profiles. It's a thing of interest. So metering and monitoring. What means monitoring? It's metering. You took n kilowatts, you should pay. Monitoring is more about a quality of energy. Voltage, frequency. On the one hand, companies are constrained by local regulation, quality. What electronic device we use in power system? Watch, I'm talking. What would I say? Monitoring. We have regulation. There are quality standards for power. Voltage should be not less, not higher. Frequency should be THD, so non-sin should be less than, and so on. First, we have our internal quality control. We should not wait, company should not wait until someone runs to government. Okay, in our case, it's a Commission for Public Services. Sabiedrisko pakalpojumu regulations komisijas. A Commission for Regulation of Public Services. Customer getting voltage too low, or for example frequency not 50 Hz, can go complain to this commission, and commission can fine power company. So company is perform internal quality control, it's one thing. More demanding, companies need to develop their future strategies, development strategies. It's good to know what happens in reality now. Not some theoretical data, maybe like this, maybe like that, but to know real picture, to understand what's going on now. Real demand, real quality, real sex. To understand problems before they, at early stage. In first seconds you can extinguish fire with a glass of water. Wait for some time and all city fire brigades can save you. So understand problems at the early stage, so monitoring devices. And of course dispatch systems. Dispatch systems are needed. It's much better to control system from comfortable office, not by running to fields and switching something manual. Okay. Let's try to understand how it works. For example, I can say kind of a process flow. Let's take an example. Simple device. What can be simple device? So overcurrent protection. Very simple device. So we have, let's say, source. What current flows if current is above allowable level. Let's say it can be maximum allowable. What should device do? Disconnection signal should be sent. Disconnect this load. This load is faulty. Simple device. Or circuit breaker. Here coil. If current is over the limit, trips. We need something, this one. For something bigger, this is overcurrent relay for distribution networks. Nice digital. I should switch it on. On overcurrent relay. sends disconnection signal if current is above allowable threshold. What we will see inside? Let's try to understand how to say process flow. What's in the input, what in the output. Busbar, switch, line, load. What's our signal? What we're getting from what we are looking for. In older model, in analog model, our signal came from current transformers. Do I have one? Here. 10 current transformer for 10 kilovolts. Has 2 cores, you see? 2 cores. One for, the bigger one is for protection, the smaller one is for metering. This one is precise, but it's only operational up to approximately 150% of rated current. Then it will separate. Large one is less precise, but it's operatable up to 40 times of rated current. Here a terminal for 10 kilovolt current. T means transformer, A amperes, current transformer. From current transformer we have signal with level rated 5 amps. In reality it has from 0 to 200 amps. In older style, analog style, we will get 5 amps. Here grounded. Transformer with rated current 1 amps. Much expensive, it's usually for high voltage network. 5 amps is more popular. 5 amps are cheaper. For high voltage network, 1 amp standard used. So from 0 to 40 amps currents. If our logic requires voltage, there are logic versions where we use voltage from voltage transformers. This signal is from 0 to 100 volts. This is what we get from primary sensors in older version. New pure digital version exists. I will draw it separately now with this. These signals are not suitable for digital processing. What we need, this victim, it's disassembled protection device. Here I can show it. It's a cassette of input signals. See? Transformers. Current transformers and voltage transformers. Here they are. You can see. Next part. Within our case, border of our device, inflow inflow 5 amp, for example, signals. What we need? We need conversion to levels suitable for microelectronics. Both 5 amps and 100 volts are too much. So here we come into initial analog signal interface stage. This stage may use interim transformers. They coordinate levels for electronics and ensure isolation between substation or object network and electronics inside. It's good for electromagnetic compatibility. You heard about AMC? Yeah, there are AMC, electromagnetic compatibility problems. Peaks, computations, all kind of computation. Interference, please. Do I have some? Not like this one. Hey. Why do they always disappear? Where's my clock away? Ah, it looks at me. Oh. Camera, come back. Look at this tiny stuff. No, it's time relay. Oh, time relay. Computation of this coil are absolutely in person. When disconnected, it's powered by 220 DC up to 800 volts spike. Computation spike when coil is disconnected, when previous relays takes off this binary one. For such relay, induces 800 volts. AMC problem is not a joke. Such spike in circuits of your digital devices, I can guarantee it will cause serious malfunction. That's why the stage also performs AMC compatibility tasks. Look what they got here. Circuits like capacitors. What else? What are these? Yeah, not simple induction coil, but so-called bipolar coils. Wait. Here should be power supply somewhere. Oh, here can see. Pair of coil on common. This is special coil to fight disturbances. This is AMC compatibility coil. Oh, two coil. Maybe I have somewhere. Don't move. It should be somewhere. Okay. two coils sharing same core. Special AMC suppression coils. So this stage, input stage, perform insulation, level, conversion, and is a line of defense in AMC problem. What next? Next moment is analog preprocessing. You cannot perform digital processing of the signal without analog preprocessing. I will show it. I will prove. Oh, interface. Next stage, in minimum it should be LPF, but it's a pre-processing. Some devices use preselectors, some analog conditioning. Also, pre-processing stage contains overvoltage protection. Like, for example, can be plus DC minus DC. Oh, no, in opposite. This way and this way. Voltage limiter. It may contain it may contain just so it may contain limiters. These are not. It may contain semiconductor limiters. It may contain non-linear resistance. Some devices do have spark plugs. Real comp gap like spark plugs in this stage. So pre-processing stage should contain OVP, means over voltage protection. Again, it's again under AMC chart. OVP, over voltage protection, is mandatory because your device should be what? Reliable, robust. Next, this analog preprocessing. Next part is ADC, analog to digital conversion. Next stage. Here also special. You cannot use audio techniques or simple metering. That's the problem. You need to first. You need ability for dynamic range, something like 60 decibel on high. You need high dynamic range, and on the other hand you need precision. Special analog to digital conversion here is special. It's good news, it's low frequency. Usually we don't use high frequencies. Bad news, precision and range. ADC, next stage, DSP. Maybe I don't. So, analog to digital conversion. Next part will be DSP, digital signal processing. From data flow of analog to digital conversion, simply measure a point. At the point of ADC, you will get what? For example, current as a function of discrete time here. 1 tau is a measuring step. This pure device used 1 millisecond measuring step. Some use higher. How to say, Gen 1 devices popular 600 Hertz measuring frequency or sampling, correct, call it sampling frequency. With sampling frequency 600 Hertz. The DSP part performs filtering key moment. Why all this about? We need to answer question current is high. Yeah? But how can we calculate this current? We use something like electrotechnics theory. Yeah? Where we operate with what? With phasors, effective value, and things like this. DSP, usually, DSP part is oriented to obtain something like current effective value, phasors, and so on, something what is inside framework of basic electrotechnics theory. So DSP part will give us, for example, phasors or models or something like something what we can compare with results of calculus in our basic electrotechnics. DSP here is also specific. That's not all. We have, let's say, currents, voltages after DSP. This is from DSP. We also may need binary signals. Input parts for binary signals contains, for example, input protection with non-linear resistance, capacitor filter, and so on. For binary signals here are in levels 0, 110 volts DC, 0 to 120 volts DC. Some may 48 volts, some use 48 volts. So quite high voltages. Binary signals need 100% in simplest way. They are opto-isolated from our system, but it's simplest way. Simple optocouple, yeah, about optocouples. Let's see, to ensure galvanic barriers, optocouple, or here, tiny optocouple, it is tiny. Late emitting diode and photosensor gives insulation barrier. It's a simplest way. More complex has a level. They ensure what kind? If your primary voltage, let's say X or Y, this system will give you nothing before mean to protect against false signal. And one, if voltage is above threshold, and also has a limiter. In case of overvoltage, it will not burn. Some manufacturers ignore these limiters. I saw burned binary inputs. So binary inputs, and that's, you think this is all? No, that's not all. When you switch something, what can be easiest binary signal? State of the switch. Here. Say hello to 24 kilovolt switch. State of the switch is a binary signal, on or off. When something happens, when neither contact makes 100%. In reality, you will see something like dribbling. To protect from false operations, somewhere inside binary inputs is a special thing, hysteresis. Something like this. Volt to go from to output from go to 1 from 0, higher voltage is required when going back, and also filter to get time delay. Signal should exist for some time. It's for AMC compatibility. So UE from DSP, it's analog pass for analog signals, binary logic go through its own path. Some strange device use ADC also for binary inputs, but usually they are conditioning or processing of such signal is performed in binary input stage, mostly with analog techniques. What next? So I have binary signals and voltage currents from DSP. Next part is main logic. For example, again, returning to one earlier, circuit breaker should be disconnected, supply should be disconnected if current is above threshold. Below threshold, it's okay. Up, we have emergency, let's disconnect. Inside logic, we can see what? In mass form, we can write some function of U1, Ui, or let's say Un, I1, In is greater than some C1, F2, 1, I1, IM greater than C2, and also it's a part for condition and also some, let's say, function binary 1 binary car is greater or something like some CK here. So we will see set of condition. In general, we will set of condition for currents and voltages, which can be defined as some mass terms, and also some constraints by binary signal. Binary part gives us additional constraint. All this inside logic, and all this came to comparison with some condition constant. 100 amps is good or not good? 1000 amp is allowable or not? We need to define somehow this threshold between OK and fault. It's done. How it can be done? By modeling. We perform network modeling, and we say, okay, we have customer. We can model fault. In case of fault, current will be, so our threshold will be. Our protection guys can tell us this line should be disconnected if current extends 2000 amps. Okay, we need to program this 2000, yeah? Where we program it? All this device should be equipped with safe NVRAM for set all this set of constant, good, no good, or function options and so on, it's all should be stored in non-volatile memory array. They should be always available for logic. Logic part needs this threshold settings. So special and non-volatile memory. Next, what do our logic? Logic determines good or no, not good. If not good, if fault, what? We need to send disconnection signal. Binary outputs. This switch requires 5 amps DC for its disconnection coil to operate. Binary outputs, here bit ruined, binary outputs custom. Depending of level, how to say, safety or robustness level, binary outputs may vary from simple set of relays to very complex redundance with strong redundance. Anyway, relay even in simplest form, relay here. And in the most easiest AMC compatibility may have also coils capacitors to prevent AMC disturbance, to prevent over voltage wave came from the output network, from the switch. Output wire from this relay goes to 24 kilovolt, for example, switch. When switch operates, AMC wave comes back, and I saw it in reality. Device trips, switch operates, AMC, this over voltage wave, cause device to reset, reclosing logic fails. Device fails, commission. So binary outputs are not so easy here. It's not a fridge or something like this. What else? We need HMI. Somehow we need to set, first we need to set this operation constants. Also, it's good for marketing. When operator, I don't know, dispatch personnel sees what device is okay or not okay, or what's going on. Especially, we have trip, we disconnected, line disconnected. Why line disconnected? What happens? So HMI, human to machine interface. HMI, human machine interface. Field of settings and state. It should be errors field settings. Here should be state. Good, okay, not okay, faulty, or device state. And one more. Nice HMI draw schematics diagram. But what also should be in HMI? See these LEDs. Array, nice array of LEDs. Common approach, even in old device. Hey, on. Come on. Okay, it's broken. Kind of this relays. So it's an indicator, trip indicator. This relays, nothing happens, we operate it. It's an event. One of the things needed, it can be small addendum to HMI, it may be part of main HMI, but it's an event. You need to indicate. Here they are programmable. First, you indicate OK. Here, programmable. Cheaper device had hard logic. Well, this device here, white space, you program your event and right here. For example, disconnection of line 1, reclosing, operation first, second, third zone, and so on. It's done for linemen, for example. Personnel who they are even don't allow to push some buttons. They came to panel, see, over current trip, line 1. Okay, lineman understands immediately. Okay, we have damage on line 1, let's go. Simple event indication. overcurrent, I don't know, reclosing, failed reclosing, one. Immediately looking on panel, red light. Ah, something not good. What's reclosing? Okay, let's go. Simple indication of events without necessity to push some buttons and so on. What else? Nowadays we need communication. We can have one port. Older devices had communications or a kind of usually serial kind of communication. So anyway, data port, what you can use first to connect your PC to what? To set settings, watch your events and so on remotely. Also, good intelligent devices allow inter-device communication. You can establish link between devices and work them in cooperation, interlocking and so on. So one DP means data port, communication model. Some devices intended for remote location use or mobile operator network or dedicated radio network. So they can be equipped with radio model. For example, here in our climate, all metering devices are equipped with mobile data model for reading, for data acquisition. Communication is must. We can speak about it. And what else? All these things needs a power supply. Power from 110 or 220 volts DC, output, all this was plus minus 15 volts for analog processing, 5 volts DC. For all the processors, 3.3 volts for newer and so on. 24 volts for binary outputs. Power supplies, also not very simple. Robustness, dual power AC DC welcomed, and a long time of operation. All this should operate 24/7 for many years. And what else? Power supply for such devices are designed with high level of EMC redundancy. Network from which device is powered is, how to say, harsh. On the same net can sit one of the, how to say, nastiest things, on coil for a large, how to say, the worst what can be 10 kilovolts electromagnetic mechanical drive with magnets, 100 amps switch on current on DC to 110. It can be the same circuit you powered from. So power supply should be AMC redundant. For device, for responsible device, you need internal source for some 5 seconds of independent operation without power. This means enlarged capacitor banks. Power supplies are specific. When I have time, some really real high-level devices has distributed power supply system. I saw it in reality. 220 DC, 220 DC, 48 volts bus 1, 48 volts bus 2, automatic rebalancing, logical part, PS1, PS2, redundant power supply system for logical part, and what most funny, BO, each binary output has its own power supply, and all this controlled by power management logic. Each binary output came with its own small power supply. It's done for super redundance. And interesting, binary output where power, not for all circuit, but for important, each circuit has two binary output, and managing system controlling one. If one fails, system with redundancy. Powers when really high level of robustness is needed, distributed power supply system, not some use from server system derived hot swap systems, but some redundant and separated with automatic select. Some protection devices have very complex power supply system, because without power it will not operate. No operation can cause serious damage. There is what to pay for. One more. Self-control logic. For simpler, for example, this one had self-control 15 operational channel. Where is? I just saw it. Oh, here is its main board. Oh, device. Digital signal processing, program memory, operative memory, NVRAM for settings. This one is NVRAM for settings. This part, analog conditioning, analog to digital conversion. Here 1, 2, 3, 4, 5, 6, 12. One of the channel is used for control, and one of the analog channel is connected to a reference source, so it measures voltages, currents, reference. If reference measurement is outside of known, we have problem in analog part. Also, setting. This one had settings integrity control. Some of all settings values cyclic redundant sum or signature, simple signature of all settings calculated periodically, once in seconds. If there is difference, oops, we got problem, device not operation. Integrity control. What's I'm missing? Time. For simple device, just timing of events. If something happens, it's good to know when. Nice thing like RTC, real-time clock. Should be redundant, should have battery backup. Simple device has just clock, but more complex devices, which interoperability is dependent on device-to-device measurement comparison, should have precise real-time clock, because they operate with time-stamped values, and error in timing may ruin. You simple, when you compare, for example, currents on two ends of line, shift in time means error in comparison. So time clock is important thing. Nowadays devices are able to communicate on network. One thing industry standard is something like this. Reception from Navstar satellites, B signal, time reference. Clocks are disciplined by navigation system signal. Next time, follow this black cable on the opposite side on the facade, two GPS antennas. Next time I take a look. Who's calling me and why? Oh my god. Yeah, так, слушай вас. Ну, я так
She will let us boil you. Last time also she helped you process and she will do something if she has.
Clocks are important. So here in short I just draw structure of relatively simple device. This guy, oh my idea. This relatively simple device. More complex devices. The most complex sets are gateways. They are very protection are important, but really protection devices now not so complicated like these power gateways. A lot of things about. Okay, we will try to look inside what's in. How it's organized. Oh yeah, one moment. I nearly forgot. I told what this idea with current, when currents are taken from current transformer, is old. $850. It's a standard framework for digital substation. In case of digital substation, things are done a bit different. we have current transformer. It's already came with analog procession, DSP, RTC, on logic, network interface, and it's connected to substation 1. Current transformers and voltage transformers are in units with own analog procession or DSP. They are connected to local area networks and they are sending time stamped measurements. Time value. They are sending time stamped measurements to local area network. All devices in on substation may do what? They are local area network connected and they take directly to the DSP second. They have own DSP next, or logic and so on, but they don't need analog part. Analog processing and initial digital signal processing is performed by current voltage transformers unit. They may be current transformer with blah blah blah, or optical sensors, extremely expensive. Super linearity, super precision, but expensive. Real optical, based on light polarization shift in magnetic field, and Poker cells used to compare. So they today we have, if we have good budget, we can switch to digital substation where primary measurement units do have their own. They came with initial signal processing stage, and they are local area network connected, so we receive time-stamped value from them. And they are shared. You can have as many devices as you want. I know, 200 devices, and these devices read, they obtain measurements through local network. It's a modern idea. You don't need to build current network on your substation. You build local area network, and data came from nice transformers with only one problem in them: price tag. Expensive. It's expensive solution. Okay. I think it's enough for today. Next time we can go stage by stage, trying to understand how it works. There are huge set of variants, but I need to look in how to say, bit general view. I'm reading this for the first time and maybe for the last time, so I'm limited with what I know. I don't know what as many companies, as many designers, as many solutions. I knew what I knew. I'm limited. Okay, I see one viewer. Maybe some questions? Good lecture. Thank you. I hope it will be better. we have skeleton device. What's inside? Well, I hope I will be able to explain what's inside and how it works. Okay. Enough for the first time. Next time will be more. Where is my ending?